Welcome to our latest deep dive. Today, we are going to explore a really fascinating paradox hidden deep within the technology we use every single day. We're going to look at how the digital world ticks in distinct, rigid steps, and how engineers and musicians deal with that reality in radically, beautifully different ways. From heavy industrial machinery to underground dance floors, it all comes down to math.
Here is what we're looking at today. We've got 1, the continuous digital divide, 2, sliding mode control explained, and 3, taming the digital chatter. Then we're pivoting to 4, modeling the acid sound, 5, the flavor of modulation, and wrapping up with 6, chaos versus control. We are starting in the dense mathematical weeds of industrial control algorithms, and somehow, by the end of this, we're going to end up on the dance floor with the chaotic sounds of acid house synthesizers. The connection is absolutely going to blow your mind.
Section 1. The continuous digital divide. Think about the physical world for a second. Things like a swinging pendulum, a spinning motor, or a sound wave. They move infinitely smoothly, right? That is continuous time. But digital computers, they just don't work like that. They can only sample information and update their commands at specific, fixed intervals. We call this a discrete time system. And bridging that fundamental gap between smooth physical reality and rigid digital steps forces a permanent, inescapable compromise on anyone writing code for the physical world.
Section 2. Sliding mode control explained. Let's see how industrial engineers try to force a physical system to behave perfectly despite this divide. They use a mathematical concept called continuous time sliding mode control. Imagine a wildly swinging system. The controller essentially grabs it during what engineers call the reaching phase and aggressively wrestles it onto a straight target line, known as the sliding motion. But here's the catch. To keep the system balanced exactly on that line, the continuous math demands an infinite switching frequency. The math says, switch the motor on and off infinitely fast to keep it perfectly balanced. In a pure mathematical vacuum, it works beautifully.
Section 3. Taming the digital chatter.
Remember our digital divide? Discrete digital controllers can't switch infinitely fast. They have a permanent speed limit based on their sampling frequency. So what actually happens when you force continuous math into a discrete time computer? You get violent, erratic spikes. Because the computer can't switch fast enough, it overshoots and undershoots the target line again and again. Engineers call this chattering. And in the real world, this aggressive, high-frequency chattering isn't just bad math. It can cause massive electrical current peaks that literally fry circuits, or it can shatter physical mechanical gears. It's digital chaos destroying physical hardware.
To stop the machines from literally tearing themselves apart, engineers had to compromise. Enter quasi-sliding modes. Instead of trying to force the system onto a razor-thin, perfect mathematical line, they smooth out the brutal math. They replace rigid switching algorithms with sigmoid functions, which are basically smooth S-shaped mathematical curves. This creates a safe, smooth-out boundary region. The system might wobble a tiny bit inside that boundary, but it's safe. It's controlled. The chaos is eliminated.
But you know, that raises a really fascinating question. Engineers spend all this time and energy trying to kill the chatter and instability. What if we took a step out of the factory and into an electronic music studio, where that kind of chaotic, unstable, hardware-straining behavior is exactly what we're looking for?
Section 4. Modeling the acid sound.
This brings us to the K303 software synthesizer. It's a discrete-time digital tool built entirely to recreate the gloriously unpredictable chaos of the legendary physical TB303 instrument, the exact sound that defined acid house. And this isn't just abstract theory anymore. The software succeeds so brilliantly at creating an authentic, gritty, analog feel that it pulls incredible praise from music critics, earning reviews that highlight how perfectly the digital code captures that aggressive hardware kick. But how do you program that organic grit into rigid digital steps? Well, the developers didn't try to make the math perfect. Instead, they mathematically modeled the actual imperfect physical components. It is absolutely wild how far they took this. We're talking about writing code that meticulously emulates asymmetric coefficients, the specific soft clipping saturation of silicon diodes, and a high-pass filter in the feedback path. They intentionally code in what they call analog drift, deterministic variations in voltage bias that make a square wave slightly lopsided and nasal. They are using advanced discrete math to painstakingly recreate the exact hardware imperfections the industrial engineers were desperately trying to get rid of.
Section 5. The flavor of modulation.
It's not enough to just clone a physical circuit, though.
The K303 harnesses that discrete mathematical power to push the sound way beyond any physical limits. Rather than just giving you a list of boring presets, the software stacks 7 escalating digital signal processing engines right into the signal path. They call this the flavor palette, and it ranges from the pure, dry squelch of the original up through Stonefish, which gives you a brutal saturation wall, all the way to Dragonfish, a hard-synced machine that fires off tearing, screaming industrial overtones. Every mode keeps the character of the one below it and stacks a new mathematical signature on top.
And if you push these algorithms to their absolute limits, you arrive at things like Angelfish 2. At this point, the math isn't just modeling a circuit, it's practically being weaponized. The digital overdrive is pushed up to a staggering 41 times gain. The filter is opened at audio rates, resulting in metallic shrieks. The resonance parameter literally tips over into a roaring volcanic scream. It's raw, aggressive emotion generated entirely by numbers stepping rigidly inside a computer processor.
Section 6. Chaos versus control. And so we arrive at this beautiful contradiction in how we model the real world inside a computer. On one side, we have our industrial engineers. They're fighting a desperate mathematical war against discrete time limits. They use quasi-sliding modes and sigmoid functions to completely eliminate high-frequency digital chatter, all to keep physical hardware perfectly smooth and safe from destruction. But on the exact opposite side, we have our music software developers. They are using the exact same digital realm, but their goal is reversed. They painstakingly code that exact chaotic instability, the analog drift, the asymmetrical clipping, the violent resonance, to capture raw human emotion. One side uses math to kill the chaos, the other uses math to worship it.
And that leaves us with a final thought to ponder today as we wrap up. If discrete digital control gives us the absolute pinnacle of human engineering, the ability to mathematically perfect and stabilize our world, why are we so deeply obsessed with programming our software to be as beautifully, noisily, and chaotically imperfect as the real world we just tried to escape?